A huge thanks to my Patreon supporters for making this episode possible. Good morning, fellow mathematicians! Welcome back to another video, and it's going to be a fun one because we are going to continue where we left off with the last physics video, where I proposed that the mass when dropping an object to the ground of the Earth actually does matter when calculating the time it takes for the two objects to collide. And I proposed that your mama, the heaviest object known to mankind, is going to drop faster to the Earth than, let's say, for example, a 1 kilogram bowling ball. And at the very end, I proposed a big ass formula that we are going to derive today, which is just a general case of a more special case I derived when talking about the collision time of 2 point masses in free space. You can find a link to the video down there in the description. And now we are going to dive right in. I hope you are going to enjoy this video. Also, video sponsored by NordVPN. You can support the channel massively by just trying them out. More information at the end of the video. And now we are going to dive right in. So at first, a bit of background information that I took out of the most prestigious book I had lying around my shelf, namely the Manga Guide to Physics. Newton's third law states that for every force there is a force with the same magnitude but with the opposite sign. And also we had Newton's universal gravitational law, where I said in the last video that we had r squared down here, where r is just a distancing function which can be expressed as x2 minus x1, where x2 and x1 are just the distances that our masses take basically during their journey to one another. And yeah, now we can start using Newton's second axiom to manipulate those equations a little bit more. Namely, on the one hand, we have that the force 1 is nothing but the mass of the first object times the acceleration of the first object. And we have the same speed here, just with a 2 as the index. So m2 x double dot 2. And one more piece of information that we need to take into consideration here. So let's suppose we have the Earth here, which goes into the positive x direction all the time. But then we have the second object right here. With regards to the reference frame of the Earth, this object is going to move towards our Earth in some way. Meaning overall that the acceleration or the distance in general is going to be negative. Meaning what we need here is a negative sign in front. And now with those two equations that we're having here, we can start adding them up. Leaving us overall, if we add both sides up respectively, we are going to get on the one hand, okay, one thing we can do in before is cancel out the masses right here. We are going to suppose that they are not equal to 0. Okay, we can cancel them out on both sides. Now we can start adding stuff up. x2 minus x1 is nothing but r, as proposed here, leaving us overall with g over r squared, and then we are going to get, after factoring out, m1 plus m2. Okay, just adding those up. And also what we are going to have is, okay, we are going to get x1 double dot, and we are going to add to it negative x2 double dot. Okay, so m1 plus m2, we are going to call this combined math capital M, just like in the last video. And also we are going to have this right here. So one thing that you need to take into consideration is that x1 double dot is nothing but the second partial or second derivative with respect to time. Doesn't need to be partial derivative, but it really doesn't matter, of x1 minus the second derivative with respect to time of x2. Since our differential operator is linear, we can actually factor it out. You could say we can anti-apply it, or we can factor it out in the space of differentiable functions. Okay, leaving us overall with the second time derivative in t of our x1 minus x2. But we know that x1 minus x2 is nothing but negative r. So this right here is nothing but negative the second time derivative in our r, which is negative r double dot. Okay, just a bit of manipulation that I want to take into consideration, leaving us overall with, okay, negative r double dot being hence nothing but g divided by r squared times m. And this doesn't seem too bad, right? at first. This right here is a differential equation which is not too easy to solve, okay? It's actually pretty bad to solve, but we are going to play physicist once again, just like we did in the last video with the gravitational acceleration, and we are going to make use of a tiny little trick here. So at first I want you guys to notice something. If we have the acceleration is nothing but time derivative of our velocity, so the change in velocity over time basically. So we have that r double dot is nothing but dv dt, okay, just as a little side note. And also we have that our r dot is nothing but our v, which is going to be dr dt. Okay, just a little bit of information that I want to put on here, because we are going to do a little bit of manipulation right here. We are going to play, and to say it in the words of Euler, physicist. Once again, I haven't done this in a while. I'm going to write everything out. So negative r double dot is going to be dv dt. And what we're going to do is we're going to expand this fraction. In one dimension, differentials can be treated as fraction, just as a little thing here, okay, that does hold with differential forms. We're going to expand this by dr over dr, and this is equal to g divided by r squared times m. And this right here is an absolutely badass trick, which works for a lot of non-linear differential equations, which is really cool. Now we are going to suppose that all those parts of the fraction, numerator and denominator, are multiplicative. Don't even want to say that, this is really ugly, but we are going to act like we can do this. And you know, 3 times 2 is the same as 2 times 3. So what we are going to do is we are just going to use commutativity on those differential forms basically. Leaving us overall with, and I'm going to put implications here, not equivalences, because it's a bit fiddly squiddly, negative dr dt and then dv dr, being hence nothing but g times m divided by r squared. And now here's the really cool thing that's going to help us solve this differential equation now, because dr dt is nothing but our velocity, leaving us overall in the process with negative the velocity times the differential of velocity in our r, being hence nothing but gm divided by r squared. And now we can go ahead and solve this differential equation. We are going to reduce it now by one order by integrating both sides with respect to r. Meaning, what we are going to do is we are going to integrate this right here with respect to r, and also the right hand side, which is going to be the integral of gm divided by r squared dr. And you can either solve this now as indefinite integrals, or we are going to plug in initial conditions already. And the initial conditions are kind of easy to find out. So as for the velocity, what is going to happen with the velocity at the very first second? So when nothing happened, our two masses, okay, if I hold this piece of chalk up, it doesn't have any velocity at all. So the velocity is 0 at the start. And once I let go, it's going to have some velocity which is going to change over time in the process, okay? It's going to accelerate towards the Earth, for example, meaning up here we are going to have our velocity r dot with respect to time. Now what about our radius? How is this radius going to change, or what is the radius overall? I mean, at first we are going to have an initial radius, which is going to be just the distance between the center of masses, okay? This is just the initial radius that we are going to have. And this was also part of the formula that I proposed in the last video. And once I let go, it's going to change its radius over time. Just like the velocity, it's going to change its radius over time. So this is nothing but r with respect to t. And now, since we can treat differential forms like fractions in one dimension, dr over dr is going to cancel out. You can justify this by doing very rigorous substitutions. I have done this so many times on this channel. Take a look at my differential equation playlist, please, to see how you can actually justify this more rigorously. But now we can start integrating both sides, because what we are going to be left with at this point is that we are going to have negative the integral from 0 to just some velocity t, or let's call it r dot. And this right here is just v dv, being hence nothing but, I mean, integrating this is fairly easy. This is going to give us negative v squared over 2 from 0 to r dot, being hence nothing but, okay, if we put 0 into here, it's going to vanish. It's a simple polynomial. And putting r dot into here is just this thing with r dot in there. So negative r dot over 2, but the whole thing squared, the r dot squared. And also, if we integrate this part right here, I mean, g times m is just a constant, we can bring it to the outside. 1 over r squared integrated is negative 1 over r, basically. So what we are going to get is negative g times m over r, and all of this, the upper and lower bounds, from the initial radius to some r with respect to t. And now, if we just consider those two sides, we can cancel out the negative signs. And also what we can do is plug in those two values, leaving us overall with nothing but g times m, multiplied with, okay, plugging in the first value is going to give us 1 over r minus 1 over the initial radius. And now we can start expanding fractions right here and solving for r dot basically in the process. Meaning overall, to solve for r dot in the process, we are going to multiply both sides by 2, take the square root, and we are going to expand this fraction, which is nothing but ri minus r divided by the product of r and ri, leaving us overall with r dot being hence nothing but positive or negative. We are going to talk about this in a minute. Square root of 2 times gm multiplied with the square root of ri minus r divided by r times ri. Whew, that's a bunch of stuff to do, am I right? I hope you can follow along up until now. And now we want to solve this differential equation because we are still not at the time basically, or just the radius in general. Meaning what we're going to do is we're going to divide both sides by this third right here, the third part. Okay, to separate the differential equation basically into a constant part and a part with respect to r, leaving us overall with, if we take the reciprocal on this on both sides, we're going to get the square root of ri divided by ri minus r times, and this right here is nothing but the r dt, and this is going to result in plus or minus the square root of 2 times g times m, and that's basically it for now. And to solve this differential equation, all we need to do is integrate with respect to t, because, well, we want to get from the velocity one step upwards to the distance between the two, okay? Meaning we're going to integrate with respect to t on both sides. And once again, we're going to play physicists because dt and dt are going to cancel out, like mentioned before. Rigorous substitutions get the job done. And now once again, what about the initial conditions that we need to impose on this problem? I mean, as for the time, it's very easy because at first, when we drop an object, no time actually happened. I mean, nothing happened, meaning no time is gone, meaning the lower bound is going to be 0. And what about the upper bound? I mean, when it hits the Earth, it's going to be just, now my chalk is rolling away, this is just going to be the time it took to collide with Earth. Meaning this is the collision time we are seeking after. And what about the upper and lower bounds for r? The upper and lower bounds are actually going to give us nice constants overall. We don't need any time-dependent function anymore after that, because at first what we had was the initial radius between the center of masses, so our Ri is the lower bound. And after all of that's done, when it hits Earth, there's just the radius of the Earth and the radius of the center of mass of this object being just the final radius, so the final distance between the center of masses, which those two are apart. Meaning this is our RF, our distance at the end, the final distance. I mean, solving this part right here is going to be extremely trivial. We are going to get a factor of t, on 0 it's going to vanish, and we are just going to end up with plus or minus the square root of 2 gm times the collision time that we are seeking after. But this part right here is kind of a bitch, and I'm going to need a new chalkboard for that. So last time I did that integral was kind of in an overkill way, but we can do better than that. It's going to be more accessible today than the last time around, I promise that. And this just has to do with the fact that we can actually make use of trig substitutions early on in this stage already, which comes in quite handy actually, because you might notice if we didn't have that Ri here, for example, if we had a 1 here, then we could substitute, for example, cosine squared as being our r, and this would make matters a bit easier because we would get sine squared down here, we would also get a cosine squared up here, and maybe with the differential we could cancel a bunch of stuff out. Since the square root on a positive interval, which it is because those radii are positive, we are going to get just sines and cosines out, cancelling a bit of stuff out. But we have one problem here, we don't have a 1 here. And here comes a trick in which I basically learned the first time around when dealing with Coxetter's integral. Namely, we are going to turn this into 1 down here in some way by introducing the substitution let our r be nothing but, and now we are just going to take the factor Ri in front of, let's say, for example, the cosine squared of phi. Really doesn't matter what you use, cosine or sine, but cosine makes everything a bit easier here in this problem. And this is actually going to help a lot. I mean, at first we are going to differentiate everything here implicitly. Then dr is hence nothing but cosine squared differentiated is going to turn into negative 2 times Ri times the cosine of phi times the sine of phi d phi overall. And now what we are going to do is we are just going to plug all the information into here that we are having right now. Meaning our integral is going to turn into. So we have square root of Ri, which we can bring to the front. No one cares about that. And what we are having now is a tiny little bit of a problem here, because what about the upper and lower bounds? I mean, we need to do some analysis here a bit. So at first, if we plug Ri into here, we're going to get that Ri must be equal to Ri times the cosine squared. What value for phi do we need to plug into the cosine such that we get Ri out on this side? I mean, if we divide both sides by Ri, we are going to get that cosine squared must be equal to 1. And on the principal branch, we can just assume that cosine of 2 cosine squared of 0 is going to give us 1. I'm terribly sorry about that. Meaning overall, for phi being equal to 0, we are actually going to get that Ri is equal to Ri on the principal branch, of course. Now what about Rf? What can we do about Rf if we plug Rf into here? I mean, there's not much we can do apart from solving for phi actually, meaning we're going to divide both sides by Ri, and then we're going to take the square root on both sides, leaving us overall with the square root of Rf divided by Ri. Okay, and we're going to take the positive square root because of the positive interval that we're having here and the principal branch, and this is equal to the cosine of phi. And now all that's really left to do is to take the inverse cosine on both sides, leaving us overall with phi being equal to the inverse cosine of the square root of Rf divided by Ri. And we're going to give this thing a new name. Let's just say this right here is the upper bound A. We are going to plug it in later in the game. Okay, this is our upper bound A, and now we can start plugging our definition for R into here, leaving us overall with the square root of, we are going to get Ri times the cosine squared of phi divided by, and now we are going to get Ri minus Ri times the cosine squared. And dr is nothing but negative 2 times Ri cosine sine and all of this integrate with respect to phi. It might seem weird now, a bit of, I don't know, more than we started off with, but a lot of stuff is going to cancel out. For example, the Ri's are going to cancel out in the numerator and denominator, leaving us with 1 minus the cosine squared. And 1 minus the cosine squared, we know, is nothing but the sine squared. Now we have the square root of cosine squared over sine squared. I mean, this is the square root of the cotangent squared. But since we are on a positive interval, since our original r's were both positive, we are going to have that the square root of the squared is nothing but the values in itself and there without absolute values, leaving us overall with the square root of Ri times the integral from 0 to a. And now we are going to get just the cosine over the sine times, and now we are going to have negative 2Ri times the cosine times the sine integrate with respect to phi. And now we might notice the sine and the sine is going to cancel out. We can bring the negative 2 to the front and the Ri into here, giving us the square root of Ri to the third power. And then we're going to integrate over the cosine squared with respect to phi. Meaning this right here is nothing but negative the square root of Ri to the third power times the integral from 0 to a of the cosine squared of phi d phi. And now we need to integrate the cosine squared. In normal case, I wouldn't show you how to do this because we did it so often on this channel already. But I still want to go into a bit of detail at least. We are going to use something that I call Phoenix integration because our integral pops up once again after doing integration by parts. So we are going to say that this right here is nothing but our integral I. And what we are going to do is we are going to use integration by parts, meaning we need to differentiate something and integrate something. I mean, this is nothing but cosine times cosine, so we are going to have the cosine and the cosine here. Now, differentiating cosine is going to give us negative sine, and integrating it is going to give us sine. Multiplying this is cosine times sine, and multiplying those together and taking the integral of it is going to give us positive sine squared. So our integral is nothing but the cosine times the sine, and then positive the integral of the sine squared. But the integral of the sine squared by Papa Pythagoras is nothing but the integral of d phi, because this is 1 minus the cosine squared minus the integral of cosine squared. But the integral of cosine squared is nothing but our integral I, meaning we can add it on both sides, leaving us overall with 2 times I being nothing but cosine times sine plus, and the integral of the phi is going to give us phi in the process. Meaning dividing both sides by 2 gives us a value for our integral I of being nothing but the cosine times the sine divided by 2 plus phi over 2. Okay, this was just a quick excursus into how to do this integral really quickly. It's a pretty elegant method if you ask me. And now we need to plug in upper and lower bounds from 0 to a. I mean, at 0 everything is going to vanish. Sine of 0 is 0 and phi by plugging 0 into here is going to vanish. And now we just need to plug in a yet again. Meaning we're going to get the cosine of the inverse cosine of the square root, and then multiply this by the sine of the inverse cosine of the square root, and all of this over 2. And what we are going to add to it is nothing but the inverse cosine of the square root of Rf divided by Ri divided by 2. I mean, the cosine of the inverse cosine is just the argument in itself, leaving us overall with the square root of Rf divided by Ri. Now we have the sine of the inverse cosine. This is a bit of work we have to do here, but it's not too bad, because what we know is that sine squared is nothing but 1 minus cosine squared. Now we can take the square root on both sides. And now if we plug the inverse cosine into here, we are just going to get that this right here is the square root of 1 minus, and what we are going to get is nothing but the argument a in itself. Okay, if we plug the inverse cosine into here, this is just going to give us the cosine of the inverse cosine. This is going to give us a squared. I'm terribly sorry, not a in itself. So meaning we're going to multiply this by the square root of 1 minus and just the square of the square root of Rf divided by Ri, and all of this over 2 plus our inverse cosine of something over 2. Now that we are done with that, we can just plug this value into what we have here, and then we are basically done. Also, I want you guys to notice that our 2's are going to cancel out, so the 2 and the 1/2 are going to cancel out here. I'm dropping my chalk a lot today. And after all, yeah, we also have the square root of Ri to the 3rd power. Leaving us overall with, okay, we're going to get plus or minus the square root of 2gm, being hence nothing but a bunch of stuff. We are going to get the square root of Ri to the 3rd power. Okay, we are going to multiply, and with a negative sign, we are going to multiply this with the first part right here without the 1/2 obviously. So we are going to multiply it with Rf divided by Ri, and this multiplied with 1 minus Rf divided by Ri. And now we are going to multiply negative square root of Ri to the 3rd power also with the inverse cosine. So negative square root of Ri to the 3rd power times the inverse cosine of the square root of Rf divided by Ri. Okay, and now that we are done with that, we can start with a few more manipulations and simplifications, because this part right here is going to turn into, okay, multiplying this into here, this is the square root of nothing but, we are going to get Ri squared times Rf, okay? And the denominator is going to cancel out. And multiplying this into here is going to give us, okay, we are going to get the square root of Ri squared times Rf, and then multiplying this with this part, so negative, we are going to get Rf squared, and then Ri and Ri are going to cancel out to just an Ri here. Now you might notice that we have Ri times Rf minus Rf times Ri times Rf, so we are going to have a common factor of nothing but Ri times Rf, and multiplying this with, and what we're going to be left with is Ri minus Rf in the normal case. Okay, I hope this is correct. And now the last thing that we need to do is write everything out. We want to solve for the collision time that I forgot here, meaning we are going to divide both sides by this, leaving us overall with the collision time, being hence nothing but, okay, 1 divided by the square root of 2gm. Also we are going to get a plus and a minus in front, and also we are going to get negative, and then we are going to get, so we are having this part, square root of Ri Rf times Ri minus Rf, And then we are going to have minus Ri to the third power, cosine inverse of square root Rf divided by Ri. And we are not completely done yet, because there is one fact missing that we need to take into consideration, namely that our collision time needs to be positive. And now let us argue a tiny little bit, because those parts down here in the denominator are positive. Okay, time needs to be positive, hence we need everything to be positive. And now, this third right here is strictly positive. This part right here is also going to be strictly positive, because the inverse cosine Rf divided by Ri, and the square root of that should be between 0 and 1 in some way, definitely. It must be. I mean, there is no way around it, because our final radius is going to be smaller than our initial radius in some way. So this right here is bounded between 0 and 1 in some way, meaning this part right here is going to be positive if we take a look at the regular cosine. So this part is positive, this part is positive, meaning we need to track the negative sign to the front, cancelling out with the negative sign, leaving us overall with a final answer of the collision time being hence nothing but 1 divided by square root of 2 g times m. So meaning we need to multiply this negative branch with this negative branch times, and now we're going to get the square root of Ri, Rf times Ri minus Rf minus the square root of the third power of Ri times the inverse cosine of the square root of Rf divided by Ri, and all of this in parentheses. And this right here is the formula that we were seeking after, and I hope you did enjoy this video. I thank you guys for watching. If you did enjoy this video, please like, subscribe, recommend channel, like if you want to support channel a bit more, but I see that great support channel on Patreon, blah blah blah. And up until the next video, I wish you guys a flammable day. Ciao!